Okay, now to see question 8.
I got it wrong.
Got it wrong?
Yeah.
Okay, that's all right. Have a look. I'll go through this one. Yeah, or you can always go back and retry and fix your answers later. Now, when you see there are two variables to solve, right? The idea is to form two equations. So this is always normally always to use simultaneous equations. Alright, and to form simultaneous equations, you need to form two equations. So you need equation 1, somehow get equation 1, and somehow get equation 2. Alright, so for this chapter, most likely when you see simultaneous equations, the first equation is normally using the original formula, and then the second equation is normally using the derivative. Alright, so let's see how we can use the original formula. So we've got this formula here, and we have a point. When we have a point, that's the x and y coordinate. So you just sub the point 113 into the original equation, into you can say a y equation, just y. Alright, so write this line. I recommend you to write this line so that you're telling yourself what you're doing. Alright, and in the exam it's very important because it's like a marker when you are checking your answer again. Okay, so you know, oh, that's what I was doing in that section. So yeah, so sub 113, you would get 13 equals to a times 1 squared plus b times 1 plus 12. Okay, continuing working on that, move the 12 over, 1 equals to a plus b. So this would be your equation 1. All right, and then equation 2 is normally the derivative, so you need to derive it. So let's find dy over dx. So it'll just be 2ax plus b. All right, and now we need to, because we learned something new, we learned about stationary points. So when you see stationary point, this means that the derivative dy over dx equals to 0 at x equals to the value of the point, which is 1. All right, so we sub x equals 1, dy over dx equals to 0. All right, so you got 0 equals to 2a plus b. So there are two ways of doing of solving this simultaneous equation. I'll show you guys. I'll show you guys both methods. So the first method is substitution. Substitutions, depending on the equation, sometimes substitution might be more straightforward, and the other one in this case will be more straightforward, which is elimination. Okay, so to do elimination, first I need to look at, is there any variable I can eliminate? And normally when you eliminate, it's either subtraction or division. Right, so it's either when you subtract the two equations or you divide the two equations. Okay, in this example, you can see that we are going to subtract them because it's two terms. It's 2a plus b. Okay, in unit 3 you will learn exponential equations, and then you will get like 2a times b. Then you will divide them. Right, you do the opposite of what the equation is. So if it's plus, then you subtract them to get rid of it. So let's just say I go equation 2 subtract equation 1. Why do I do equation 2 subtract equation 1? What do you think?
Because it's larger. Like you got 2a?
Yes, correct. I look at 2a here, I look at 1a there, so I will take 2a minus 1a, right? And then the b minus b will be gone. I'll just actually write the operation here. So that's the equation 2, and equation 1 looks like this. Alright, when you subtract that, b minus b is 0, and there's nothing, so 2a minus a is just 1a, 0 minus 1 is negative 1. Bam, instantly you get negative 1 equals to a. So normally, in normal cases, you would need to solve a little bit more, but in this case, just 2a subtract 1a, that's just gone. But normally, you need to take one more step to solve for a. So that's elimination. Substitution, you need to change one of the formulas. So in this case, let's say I try to solve for a again. So from equation 1, I would change that. So I'll write a second version of equation 1. I'll make b the subject. 1 minus a equals b. Okay, let's say this is the blue equation 1. And so in the substitution method, I need to sub the blue equation 1 into equation 2. So note that if you're doing substitution, you need to make one of them the subject, right? And then you substitute into the other equation. So you've got b equals to 1 minus a. That means that when you sub into 2, you'd get 0 equals to 2a plus, and instead of b, it will be 1 minus a. Okay, so then you got 0 equals to 2a minus a is 1a plus 1, so negative 1 equals to a. Same thing, same answer. Alright, so the two methods should yield the exact same answer, just depends on what you're more comfortable with. Sometimes substitution is easier because you get the one of them is a subject straight away. But in most cases, elimination will be faster. Okay, so once you've got this one, then you just need to go sub a equals to minus 1 into, just choose an equation. I'm going to choose equation 1 because then it's just a simple a. So then you get 1 equals to minus 1 plus b. So move the 1 over, 2 equals to b. Okay, and that's it. Let's make the final answer. Therefore, a equals negative 1, b equals 2. Okay, so this is 19C question 8. Any question? No, Sarah? Yeah, you guys did this question last week. Yeah, you guys did a more complicated one where it's A, B, and C. Remember? And then there were 2 points. You sub one of them in, you get C. So this is actually an easier one. All right, let's move on. Now 19F is the one that I think was the 19D. 19D question 11 I think was the one that is a little bit trickier for everyone last week. So this question is a bit different. I think last week you guys learned the table.
Yeah.
Right? The stationary point table. So this one you will use the table but in a slightly different way. You don't have to sketch the graph, but that's actually no, you do have to sketch a graph. So this one covers everything. You didn't see question B there. But yeah, I picked this one last week because it has question B, sketch the graph. So this is 19D. 19D. So 19D question 11. We have an equation, find the value of x for which, so note the first 3 questions. Look at the structure of it. It's just find when the derivative is less than 0, more than 0, and equals to 0. Alright, so it's less than, more than, and equals to 0. To solve less than or more than, you need to solve equal first. So actually this question is a little bit strange. They should have asked the third one first. Yeah, because you need to find when the derivative equals to 0 and sketch it in order to find when it's more than or less than 0. So let's solve for A3 first. Okay, I will solve in a kind of reverse order. I'll do A3 first. So to solve for f dash x equals to 0, you need to find what f dash x is first. So that'll be 3x squared minus 6x. Alright, and then set that equals to 0. Take out the common factor 3x, then you get x minus 2. Okay, no factor law, x equals to 0 or x equals to 2. Okay, any question at this point? Now, everything makes sense so far? Remember this from last week? Okay, yeah. Now, so now that you've got the 2 x values, we need to make the table, right? What are the 3 rows in the table? What are the labels for the 3 rows in the table?
You have x.
X is the first one, yes?
Y.
Not y. We're finding the gradient table.
Gradient.
Yes.
And the little line.
Yep, you do need a little line, but let's just have the labels first. What's the label here?
The derivative.
The derivative, yes, f dash x, and then what's the last thing? The thing that helps us find out.
The shape.
The shape, yes, the shape of the gradient. Of the graph. Okay, so how many columns do I need here?
You need like 1 on either side.
Okay, 1 on either side.
Of like the 2 stationary points.
Yes, 1 on either side of 2 stationary points. That's a good description. So 0 and 2, and then you need 1 on either side. All right, and what can I fill in first?
The stationary point.
The stationary point. The derivative is 0, and the shape is
straight horizontal.
Straight horizontal. That's right. What point, Charlie, would you pick before the point 0?
Maybe -1.
-1. What point would you pick in between?
1.
1. Sarah, what point would you pick after? 3. 3 is a good one in this case. The reason why I will pick 3 is because of this part here. Remember last week I did something like 10, so that it's a bit easier to work through. But then in this case we already factorize it, so we can actually substitute into the factorized version. So anyway, let's calculate negative 1. So let's just work it out on the side here. F dash of, actually we will work at the bottom. So f dash x, let's rewrite it. Rewrite the factorized version. So when you're calculating the derivative value, right? The factorized version, aka this one, is going to always be a lot easier to work with. Yeah, because the last step is multiplication. So the last step is the one that makes the number big. Okay, as opposed to this one where you make the number big first and then you subtract to get it smaller. Nah, so you want to do the multiplication as the last step, because that would be the easiest step to it will make the number the biggest. So anyway, so let's calculate the three of them. So f dash negative 1, f dash of 1, and f dash of 3. Okay, so f dash negative 1 would be 3 times negative 1 is negative 3, and then minus 1 minus 2 is times minus 3, so actually that would be 9. Alright, then the shape would be going up. Yeah, because gradient is positive. And then f dash of 1 would be 3 times 1, which is 3, and then 1 minus 2, which is minus 1, so that would be minus 3. So the shape is going down. F dash 3, so 3 times 3 is 9, and then 3 minus 2 is 1, 9 times 1 is 9. It's going up again. Okay? So yeah, so as you can see, the factorized version is a lot easier to work with. I don't like to do with the other one, so I'll show you what happens if you use this formula here. So sub 3 in, it will be 3 times 3 squared minus 6 times 3. Now this one is not too bad. It will be 3 squared 9, 27 minus 18. Sure, you guys can all do this subtraction, but if you make a mistake in this one, GG. Alright, it's like 27 minus 8, 27 minus 8 is not hard, but it's a lot more prone to error than 9 times 1. Surely you can't mess up 9 times 1. So always factorize your function first before you substitute values in. Okay? So yeah, so now let's answer question question A3. Find the values of x for which f dash x equals to 0. Therefore, f dash x equals to 0 when what? X equals to 0 or x equals to 2.
So we didn't have to draw the table for this question, but it's just like to see.
Yes. So technically at this point here, right? So have a look. At this point here, this is the end of A3. Right? The table is actually, let's do A1 and A2.
Yeah.
Yeah. So at this point, we'll be like x equals to 0 or x equals to 2 is like the end of A3. So technically this one I can write, we're working on A2 already. Okay, so let's just say we're working on, A1. Let's start from A1 first. So when is the derivative less than 0?
When it's between, like not including, what's it called? 0 and 2.
Yeah, that's right. So you think it's between 0 and 2 because it's going down between 0 and 2.
Yeah.
Right?
Wait, are we doing 2?
A1.
Oh,
yeah, so just write so once you've got the table, it's just essentially reading out the answer. So f dash x is less than 0 when x, when it's between two values, when it's sandwiched between two values, you always use the format 0 less than x less than 2.
Yeah.
Okay, if it's sandwiched between two values. So 0 less than x less than 2, make sure it's not less than equal to, it's just less than. Yeah, because it's strictly, so they ask for the derivative strictly less than 0 here. Okay, so Sarah, when is it going to be strictly more than 0? F dash x is strictly more than 0 when?
I don't know how to say it.
Okay. Alright, if it helps, imagine this way. So see this shape there, it's like going up, going local maximum and then local minimum, right? Like imagine the shape looks something like that, roughly, right? Roughly something like that, and at this point, this is when x equals to 0, this point is when x equals to 2. I'll write 0 and 2 here. And you can just read the graph from this point. Hopefully that helps. So the derivative is, is more than 0, aka the graph, it's like coming up here and here. So how would you read the region here?
Less than 0.
Yes, so when it's like two separate sections, so see how it has this one here and then this one here, right? It's like two separate sections. It's not continuous. So you need to say the two sections separately. So the first one is x less than 0. Yeah? Or, what's the second one?
X more than 2.
X is more than 2, yes. Okay, so that's when the derivative is more than 0. Okay, alright. And then question B, sketch the graph. So to sketch the graph, you need to also find, okay, I'll give you guys a quick recap here. So sketch graph means once you've got the stationary point, you need to find the coordinates of stationary points and then the axis intercepts. That's it. Basically, it's just two things. So when you see coordinates,
But
it's x and y.
The original equation, right?
Correct, to find the y coordinate.
How do I find the x-intercept though? Because when I substitute in for 0, then I get like x cubed minus 3x squared. So do I like...
Factorize. Yeah. So fx, so I'll rewrite here, fx is x cubed minus 3x squared. So to find coordinate of stationary point, just sub the x value in. So f0 will just be 0, and then f of, what was the point again? 2? F of 2 would be, so I'm not so if I want, I can factorize it here. X squared.
No, I'm not talking... Okay, I get how to do that, because that's like coordinates.
Yeah, you're doing the next step, right? The intercepts.
Yeah.
Yeah. So yeah, I'll just factorize it, and then that actually helps me doing the intercept later. So f2 would be 2 squared, that is 4, and then 2 minus 3, which is negative 1, so that's going to be negative 4. Okay, so I would have the two turning points. So this one would give me 0, 0. If you have done enough questions, I don't even bother working the y-intercept because this is the y-intercept. Yeah, any graph that goes through 0, 0, then that point is both the x and the y-intercept. Right? If you solve for the x-intercept later, you also get 0. Does that make sense? Because it goes to the origin, 0, 0. And that is both the x and the y-intercept. Because that's a point. That's the only point that is on both the x and the y-axis. Okay?
Yeah.
Alright, and then this one would give me 2 comma negative 4. So let's just say if I were to solve for the x-intercept, because I already know what the y-intercept is, it's just 0. So let's solve for the other x-intercept.
So would you factorize first, so it's like the same as the other one, so it's x squared times x minus 3.
Correct. So then you set 0 equals to x squared times x minus 3, and after it has been factorized, it's just no factor law. Alright, so to work it out fully, it will be x squared equals to 0 or x minus 3 equals to 0. Anything squared equals to 0, that number must be 0, and then the other one is just 3. So yeah, as I said earlier, there will be one x-intercept that is 0, and then the other one will be the one we just found, which is 3. Alright, now let's sketch it. Let's look at all of the x values. Right, so the x values are 0, 2, and 3. Okay, and the y values is just 0, negative 4. Oh, actually, 0, 2, and 3. So y-intercept, the y value will just be negative 4. Alright, that means on the scale of the x-axis, it will be 0, negative 4. So I'll put it up here. 0, 0, 2, 3, so 1, 2, 3. There's no x value that's more than 3. So 1, 2, 3, and the y value is we have a point at 0, 0, which is the origin, and then we have a point at 2, negative 4. So I'm going to put negative 4 down here, and then 2, negative 4 is at this point here. So so these two will be the turning point, and then the x-intercept will be at 0, and then at 3. Alright, so it will be that one. So I know roughly it sort of looks like that.
Yeah.
Okay, now I just need to draw it nicely. Alright, so first I'll connect these two, and then this one is the turning point, so it comes up, passes through the x-intercept and keeps going, and then this one just keeps going down on this side here. Okay, and make sure you fill in the rest, so like y, x, This is the function fx. As if you have a label, just write fx is fine, and then you can put the coordinates in. So the origin is obvious, so but put this one in 2, -4, and also the other point is obvious. So if you did your teacher mention anything about using colored pens in the exam? Is it allowed?
Yeah, you're allowed to, like, you have to, like, do your actual, like, equations with, like, black pen or blue pen. But then you can, like, use a red pen, I think, or, like, a different colored pen when you're doing, like, graphs. If there's, like, multiple things on it, so it's not confusing.
Yes, that's right.
And
That's
you can
also my
also-
recommendation.
You
Yes.
have a highlighter as well.
Yes, that is
For
correct.
questions.
Yep, that is correct. That is absolutely the correct advice from your teacher. Okay, use multiple colored pens. Normally, I like to draw the graph in pencil because if you mess up, you can drop it out. Or don't use friction pen in the exam. Okay, whatever. If they leave in the trunk of the car and it's too hot, it will heat up and the friction pen is gone. So use pencil. But the point. So let's just say if I were to use pencil to draw the graph, if I were to redraw that graph, it would be like that, and I draw like that. Right. Now the points I will put in colored pen.
Yeah.
Okay, just to distinguish, and it also help me as like a drawing guide, and then I can draw like using a pencil, draw nice lines first, and then after that I color that in like that. Okay, but the points, and you can even label the points in pen as well. Yeah, so the idea is it's like the different colors will show the examiners exactly what they're looking for. Make it easy for the examiner, they'll give you more marks. Subjectively, they're not allowed to give preferential treatment. But if you see a paper, that's it's so clear, it's so easy to mark. Take easy, more easy it's easier to get marks. Okay, so that's 19C and D. Okay, any question? Yeah, everything makes sense so far. So these ones are all complex familiar questions. Not too complex, right? Not too difficult. It is complex. Right, I will not deny it is complex, but it is not as difficult as the complex unfamiliar that we're going to do today. So first we're going to go through 19E. Applications to maximum and minimum problems. Okay, alright. I'll go through the examples first and then I'll pick a similar question to the example for you guys to work through. There are some complex unfamiliar in this chapter. We'll see if you guys are up for it. Okay, so this is 19E. At this point, there's not much theory to go through. It's just seeing different ways of solving questions and then just do enough questions for yourself, and then you'll be able to do more questions in the exam. So I think you guys have gotten to the point where theoretically, we've covered the basics of everything. Okay. Now it's like those things where the more tools you have in your toolbox, the more problems you can solve in the exam. So from now on, it's just the matter of how many questions can you guys do at home. Okay. Legit. The more questions you do at home from now on, you guys already know everything. The more questions you do from now on, the higher your exam result will be. I guarantee that. There's nothing else to learn. You guys know derivative, you guys know product rule, chain rule, quotient rule. Your classmates haven't even learned those things yet, and you already learned like up to the maximum, minimum stationary points, types of stationary points. You guys already understood what I meant when I said those terms, right? So that's it. Okay, that's it. And trigonometry, unit circle, all that stuff. You guys already knew all of that. Now from this point onwards, it's just do as many questions as you can. Okay, the more questions you do, the higher your score will be. I guarantee that. Okay, it's so important that I'm actually repeating that again. So let's try. Let's have a look at example 8. When you see a question like this, so for these chapters, right, what's more important is not the answer. What's more important is listening to my train of thought. So I'm thinking aloud. If I see a question like this, how would I think in the exam? That's the more important thing. Because in the exam, you never see any of these questions again. It's always going to be different. Right? So it's not the answer to the question that you're interested in, it's how I get to the answer, what I think, what I pay attention to. Okay? So let's read this question. So I'll read the first pass. A loop of string of length 100 centimeters is to be formed into a rectangle. Find the maximum area of this rectangle. So first I see numbers, right? I think about, the length is 100 I connect the length to 100, and it's a loop of string. In my mind, mentally, I think of it as it's like some sort of string like that. Okay, you may not want to draw it out. For me, I like to draw it out because on the draft paper, it's easiest. But yeah, so loop of string, it's just some sort of string like that. So it's one line formed into a rectangle. So that one will be formed into a rectangle or something like that. Okay, and then find the maximum area of this rectangle. All right, maximum area. So what's the area of a rectangle? It's the length times the width. Right. So so this area in my mind, actually not even in my mind, in the exam, I recommend you guys to write as many things as you can. So let's just say I'll divide this section into two. So the left hand side is what I write in the exam, the right hand side is the draft paper. Very important, what you do on the draft paper determines whether you can do the questions or not. So string, all right, string, right? String like this, and then the length equals to, so length, okay, actually yeah, length equals to 100. Okay, let's say we write that, and then form into a rectangle, so I'll draw a little rectangle, then maximum area, so max area. And then area would be equals to length times width. Okay, so let's say in the exam you might write something like this. Now, have a look at the draft section that I'm drawing here. There is something that I would change in the exam. If I get to this point, there's something that I would change in my draft because it might confuse me. Which one do you think?
Like making the area have only one variable, like not having length times width, having like.
Yes, so that's a way to solve it. But so I'm talking about something slightly different. You see this L and see this L? Are they the same? Are they the same?
Yeah.
They're not the same.
Well, as in like the L is the same.
I mean, the L's are the same, but they denote different quantities. Okay, so in the exam, you might make this mistake initially when you're writing. And actually, for complex unfamiliar question, it's very common. They say length like 3 times. They mean 3 different things. Okay, so when you see something like this that could be confusing, the easiest way, the best way is to recognize, oh, hang on, this is not the length of the rectangle, right? Because the length of the rectangle is only one side, but this length is like the whole thing. It's like one string there, right? Start and end. This whole thing is 100. So when I see something like that, actually, I wouldn't write L. I would scrub it out because if you don't want to rewrite it, you can just cross it out and I'll write total length. Okay, so that step there, trust me, very important. It clarifies a lot of confusion. Okay, so if you use like variables that sound familiar, one of them you have to use a different name for it. So in this case, I'll write total length equals to 100. Now that makes sense, right? And then the L down here is the length of the rectangle. Does it make sense? Yeah? So very important. This is actually an exam technique. Very important to make sure you distinguish between the different quantities, right? Same variable is supposed to mean the same thing. If they mean different things, you have to, like use a different variable or use a different term to denote that. Okay, anyway, so I've got the area here. Now let's see. So in order to solve it, I would need to form one equation, right? And in order to solve for an equation, I would need to just have one variable. So yes, Charlie, you're right. You would want to write the width in terms of the length. Yeah. So what do we know about the total length? Total length is 100. That means
the perimeter is 100.
The perimeter is 100, right? And so how do we work with that? So perimeter is equals to 100. How do we work with that?
You substitute 100 into like an equation. It says like 2.
Yep. So what's the equation? What's the formula for perimeter?
2 times length plus 2 times width.
Yeah, 2 times length plus 2 times width equals to 100. So see, right now I'm still on my draft paper. I'm not actually running into the exam paper yet, right? Because I want the exam paper to be as neat and tidy as possible. But now I've gone somewhere. I've got 2 times length plus 2 times width equals to 100. But is there a more convenient way to? Actually, no, I think this point we're fine to continue here. Okay, so let's say what I would write. I would choose what to write in the actual exam, And what I'll choose to write is total length equals 100. Therefore, 2 times length plus 2 times width. Actually, I'll redraw the rectangle here, length and width, right? So then I've got 2 times length plus 2 times width equals to 100. This is the time to write neatly and make everything make sense, right? And then I would divide everything by 2. So then I get length plus width is equals to 50. Right? And I know what my plan is. My plan is to make W, the width, the subject, so that we just solve for the length, for example. So width is 50 minus length.
Are you doing it so that, okay.
It doesn't matter. You can make length the subject either way. Okay, and then I would have area is equals to width, length times width, which means it is length times 50 minus, all right, A for area, 50 minus the length. So area equals to 50L minus L squared. Okay, does it make sense so far? Yeah? Now, so let's say if I get up to this point, I'm like, okay, I've got something, but how do we find the maximum area? All right, now this is a new concept. How do we find maximum area? When you see maximum, you think stationary point, which links to, all right, maximum is a local maximum, which means it is a stationary point, which links to derivative. Right? Okay, this is the new concept here. So up to this point, you guys may get up to this point in the exam and be like, oh, I can get up to here. You probably get half the marks, right? But the rest of it is actually is the calculus part of this chapter. So maximum means it's a stationary point, and in order to find a stationary point, you need to find the derivative, set that equals to 0. Which is the concept of the last chapter. Okay? Now, sometimes it might help to look at the formula here. What's the formula for area? What does that look like? What kind of equation is this?
A quadratic.
It's a quadratic. So what kind of quadratics?
What do you mean, what kind of quadratic?
2 times. Concave up, concave down.
Concave down.
Yes, it's a concave down quadratic. Do you think you can sketch this?
Mm-hmm.
Yes, but what I mean is, can you sketch it in a coordinate? Is it finding the x-intercept?
You could probably find the x-intercepts, yeah.
Yeah, you can find x-intercepts, right? What do you think it will be?
0 equals 50L minus L squared.
Yep, on your graph paper, you would try to solve that, and then...
What's it called? It either equals 0 or 50.
Yeah, 0 or 50. You take 50 L out as a common factor, so length would be either 0, which is rejected, right? Or length would be 50. So now that we've noticed, then we can put in 0 and 50 and just basically do a bit of a sketch here.
Yeah.
Right? Yeah? So, okay, so this is the graph for the area. So you see the maximum area occurs at this point here. This is the maximum area. Does that make sense?
Yeah.
Yeah? So this is 0, this is 50. What do you think is the length at the maximum area? So note that this graph is A against L.
25.
It's 25, yes, that's the point in the middle. But so that's what you can do on draft paper, right? And if you want to convert that into your actual answer, that's okay. But the preferred way to do it is using derivative. So you solve for dA over dL, and that would be 50 minus 2L. Mm-hmm. Right?
Equals 0.
Yes, max area. Therefore, dA over dL equals to 0. Right? So then 0 equals to 50 minus 2L, and then 2L equals 50, so the length would be 25. Yeah? And then because of that, then width would be, so 50 minus 25 is also 25. Alright? And so the maximum area,
Wait.
Mm-hmm.
Okay, yeah.
Yeah? So max area is just 25 times 25, works through that.
This is not a rectangle, this is a square.
It's a square. A square is a rectangle.
No, they lied.
No, the square is a rectangle. This is year 9 concept, guys. A square is a rectangle.
That is not what my teacher has taught me.
They just haven't. They just didn't go through the.
Dirty little liar.
Okay, that's actually quite funny because. Yeah, I don't think teachers actually mentioned about these things, eh?
When I think of a rectangle, I do not think of a square.
Now, let me explain why. Define rectangle. Rectangle has is a four-sided shape, right? And then has four right angles. Right, four right angles, right? That's what you think of when you think of a rectangle. It doesn't. There's nowhere in the definition of a rectangle that says that the length is more than the width. Nowhere that said that. It's just any shape, four-sided, and four right angles. You cannot draw a rectangle without having these two properties, right? But these two properties is also applicable to a square. Because a square of side 1, for example, it also have four-sided and four right angles. So a square is also a rectangle. It is a rectangle. Is a special rectangle.
So our teachers are just setting us up for failure.
No.
Well, they are.
I mean, mathematically, this is something that they might have covered briefly in the past. Maybe no.
They always say a rectangle is like four-sided, four angles, and then it's got like two pairs of like sides of equal length.
Well, they will get, yes, two pairs. So look at this. The top pair, right? This is one pair, right? They both equals to 1.
They're different.
And then these two pairs are also equal. So you see, the definition of the rectangle applies to a square. So a square is also a rectangle.
They always say it has to be different. I don't know why.
No, they actually don't say that.
That's what our teachers like said when we were learning like shapes and like geometry. They were like, "This is a rectangle."
Okay, I wonder which teacher said that. Go on TikTok and check for yourself. Is a square a rectangle? The answer is yes. A square is a rectangle. A square is a special rectangle. It's similarly a rectangle. You know what a parallelogram is, right? A rectangle is a special. Eh?
It's like that.
The slopey one, yes, is a special parallelogram. Okay, a rectangle is a parallelogram. Because what's the definition of parallelogram? This one just need two parallel, two sets of parallel sides, right? Two sets of parallel sides. Okay, because normally you would see like this shape here, right? Like because these two are parallel, and then these two are also parallel. Now, when you look at a rectangle. When you look at a rectangle, this is your normal rectangle. These two sides are parallel because they're perpendicular to the other side, and these two sides are also parallel. So a rectangle is also a parallelogram. You guys learned Venn diagram, right? Like this thing, yeah, this Venn diagram thing. So,
I don't know what that is.
Wait, what? Okay, so let's say this is.
When you say Venn diagram, I think of like the two little hoops, and they
Yeah, like that, right? So that's the Venn diagram they use to teach you guys. But in math, there are different kinds of Venn diagrams. So let's just say I call this one the Venn diagram representing all quadrilateral. Okay, I'll just quickly go through this one. This is like grade 9 stuff, but it helps you guys understand the trickier bits in mathematics. So quadrilaterals is any four-sided shape. Make sense? Yeah? So inside a quadrilateral, you would have the biggest section would be a square. The biggest section would be. I can't remember. I think quadrilateral is actually the biggest one. So let's just say we have a circle that represents all parallelogram. Parallelogram, because then you have a special one here, which is like the what do you call it? Oh, actually no. I think we'll simplify for you guys. So let's say this one represents all parallelogram, right? And because a rectangle is a parallelogram, it will be a subset of this thing. Right? So a rectangle is a parallelogram. Yeah? And then inside the rectangle, there will be another one for a square, because a square is a rectangle. So this shape is in that little circle, right? But then this shape, which is a rectangle, is not in the circle that contains a square. And outside of the rectangle, you have a normal parallelogram, which is neither a rectangle nor a square.
But I thought a rectangle was a parallelogram.
Rectangle is a parallelogram,
But
yes.
you just said it wasn't.
No, it is. It is a parallelogram.
But
Because it
that's
has two
what I said.
parallel sides.
Why did you say it's not?
It's inside the parallelogram Venn diagram.
Okay.
Okay, you know what? Let's skip this one. Okay, just remember, as long as the definition applies, the shape is considered another shape. Like a rectangle is a quadrilateral, right? Because it has four sides. A quadrilateral is any shape that has four sides. A square is a quadrilateral. So when you understand quadrilateral, it's like, oh, it makes sense. It covers everything that has four sides, right? And parallelogram is a definition that covers anything that has four sides and two sets of parallel lines. Anything that has two sets of parallel lines and four sides is a parallelogram, which includes the square and the rectangle.
So everything's a parallelogram,
No, not everything. A rhombus is not a parallelogram.
isn't it?
No, it's a rhombus definition is four.
Oh yeah, that's that.
Yeah, something like that. So then actually not parallel. The sides are not parallel. It's like a kite shape is not a parallelogram, right?
What's the weird square, slopey square?
Slopey square, you mean a trapezium?
That.
Yeah,
No,
it's
not a trapezium. The slopey square. It's just like a square that's been like. It's got like a different name. It's not a parallelogram. It's like a
that's
rhomboid. I don't know.
yeah. I think so. A rhomboid, like the one where the four sides are equal, right? It's sloped, right?
It's just like a square that's been like.
Yeah, that is also a parallelogram because it has two sets of parallel sides. Anyway, so that's geometry. We'll potentially get to that in unit 4, but for now, let's move on with 19E stuff. Okay, so all right, so that was example 8. Now you guys try question. Let me see which ones are the most similar to that one. Okay, let's start question 1. It's like the exact same thing. Okay. It's like the exact same thing, but see if you can figure this out by yourself. Just give you guys some time and then I'll go through the full answer. Alright, I'm gonna slowly walk through this question now, and when I'm done, I'll start explaining it. So similarly, I will use two columns. The left column is my actual working, the right column will be my draft paper. Yep. Okay, did you get 2500?
Why do you do the derivative?
Because maximum area means the rate of change is 0 for the function. So this is the one that you need to get used to. The idea is that when you're trying to find the maximum value, it's like finding the local maximum, right? So to find maximum, right, which is essentially a stationary point, it's a stationary point, then you need to set the derivative equals to 0. Same with minimum. So this chapter is all about maximum and minimum problems. So that's why you need to derive it, set the derivative equals to 0. So this is the straightforward way to do it without having to sketch the graph. So that was question 1, should be straightforward. Now question 2 is not too straightforward. Alright, Charlie, what you missed is just the idea that maximum is when the derivative equals to 0. It's just a stationary point. Yeah? So, given that, can you guys try to do question 2? Before I go through it. There is an example similar to question 2, but see if you can work this one out first. Because it's actually very similar to question 1. I'm going to slowly start working through it. The hint for you guys is you need to define a new variable that represents the product of two numbers x and 10 minus x. Alright, you need to define a new variable so that you can create an equation for yourself. Because maximum value means you need to derive it and set it equals to 0. Okay, so the strategy, make an equation and then derive and then set derivative equals to 0 and then solve for x, and then you can find the maximum value. Okay, I'm going to work through this now. Alright, I've got the answer. Are you guys still working on it? Still working on it or finished already?
No, finished.
Not finished yet?
No, I finished.
You finished it? Sarah? Yeah? Okay, let me give you guys some interpretation of this answer before we move on to the next example, which is going to be a little bit harder. So, what is the implication of this? So when you see these two values, right? Actually, this one has a real life application. Two values, x and 10 minus x. It's very similar to the other one, right? It's like the total length is like 100. So half of the length is 50. So the width is always going to be 50 minus the length. Alright? So if you have two numbers, what they're saying is this. If you have two numbers, right? And they're defined by a certain restriction that they must add up to a certain value. So when one decreases, the other one will increase. Yeah? Make sense so far? Yeah. Okay. Actually, use an example. So let's just say we have two numbers. So this thing here, 10 and 10 minus x, means that so two numbers that add up to up to 10. Right? Because if one number is 4, the other one is 6. If it's 3, 7, 2, 8. So two numbers are up to 10. This one, what it says is that there is a maximum product of them, right? The maximum value is always going to be when the two numbers are exactly equal. What does that mean? It means that if you are faced in real life with a scenario where you have like a string, right? You have a string, and you want to form some sort of like, you know, rectangle or square. Let's say you want to form a box, right? With a certain area. What is going to be the biggest box that you can form? The biggest one is the one that is going to have a square base. If you're restricted by, you know, how by the total size of the box from the top down by the perimeter. Okay, the biggest one is always going to be a square. So if you have a string, to make the biggest area is always going to be a square. So that's the implication of this question here. Okay, so yeah. All right. So moving on, let's try the next example. So we're doing example 9. Now this example is a bit different, so pay attention. You may very well get get the exact example of something very similar in the exam, because when you see this question in the exam context, people freak out. Like, I swear, people freak out so much. Like, oh my god, I don't know how to deal with this thing. Like normally you see y equals to x, and what is this x squared plus xy minus y squared? They have no idea where to get started. It is a very simple concept, but you know, like they throw you an equation that you've never seen before, and people start to panic. So have a look at example 9. Given that x plus 2y equals 4, calculate the minimum value of this thing. So they want the minimum value of this thing. So remember, minimum, maximum, when you see that, you think stationary point. Alright, see minimum, you think stationary point or turning point. Right? So when you see stationary point, you think derivative. And to calculate the derivative, you need an equation. Okay? Now, but remember, when you derive, you need an equation with one variable only, with one variable to solve. In this case, we have two variables, x and y. So how do we get just the one variable?
You use the first equation?
That is correct. You use the first equation, and then you make one of them the subject. In this case, I actually make x the subject. Yeah, I'll make x the subject. So let's start that. X plus 2y equals to 4. So actually, I'll rewrite the steps. At this point, I know that the steps will be make x the subject, and then sub into, and then make equation. Right, or define an equation. Define equation. And then sub x into it. Sub x in, and then the rest is the same. Derive, set equals to 0, solve for x. Alright, so for x, and then you find the minimum value. Okay, so let's follow this chain of thought. Make x the subject, define the equation, sub the x value in, and then derive, set it equals to 0, solve for x, and then you just sub it in to get the minimum value. Let's follow this chain of thought. So first, make x the subject, x equals to 4 minus 2y, and then sub x into the equation. Actually, we need to define it first. So let p for polynomial equals to x squared plus xy minus y squared, and then sub x into p. So then you got p equals to, instead of
the derivative or the original polynomial.
So the idea is that you sub x in to get an equation with one variable. Alright, we're still forming the initial equation, the original equation. Okay? Yeah, we're still trying to form our equation. We don't have our equation with one variable yet, so you can't actually derive it. So we want an equation with just the one variable. Okay, so sub x into p, and then you've got p equals to So we know x is 4 minus 2y, so it's going to be x squared, which is 4 minus 2y, everything squared. And then plus 4 minus 2y times y, and then minus y squared. Okay, does it make sense so far? Sarah? Yeah? Charlie? Mm-hmm. Yeah? So now we've got this equation, we need to expand it. How do we expand 4 minus 2y everything squared? What's the formula? What's the formula to expand sums or products? Sums or differences of perfect squares. So what's a minus b everything squared?
It's I think the final one's 16 minus 61 plus 4y squared.
Like that's a simplified one?
I think so.
Probably, but I'm just going to show you guys how to expand this one quickly first. A minus b everything squared is a squared minus 2ab plus b squared. Remember this one? Mm-hmm. Yeah, Sarah? You have to memorize this like very well. You use this like a million times from now to the end of year 12. So then this would be 4 squared minus 2 times 4 times 2y, and then plus 2y squared. 2y everything squared.
Yeah.
Okay, and then expand the other one, that will be plus 4y minus 2y squared minus y squared. Okay, so let's simplify that. 16 minus 16y plus 4y squared plus 4y, minus 2y squared minus y squared. So let's just combine like terms. Like terms are 4y squared minus 2y squared minus y squared, which is just 1y squared. Alright, and then minus 16y plus 4y is negative 12y, and then plus 16.
Mm-hmm. And so then would you factorize?
Yes, you would factorize them. So let's see if we can factorize this. So ACB table on the draft paper again, ACB, so times to 16, add to negative 12. Okay, let's see. 16, let's try a few. 2 times 8, not quite right. 4 times 4, not quite right. You may not be able to factorize this, now that I'm looking at this. Mm-hmm. Okay, that's fine if you can factorize it, and then 1 times 16. None of this will add up to negative 12. Okay, that's alright. If we can't factorize it, that means that you just gotta so normally, okay, so the reaction to factorize it is good if you need to sketch it, but in this case we're finding the minimum value. So let's have a look at the plan again. You derive it and then you set it equals to 0. Alright, we're not setting p equals to 0. You have to derive it first because we're trying to solve for x to find the minimum value.
You're finding p dash.
Yes, p dash basically.
And then you substitute in 0
for p dash, yes. Okay, so let's write p dash equals to 2y minus 12. Right, now then it's a lot more simple. So then sub 0 into p dash, 0 equals 2y minus 12. Then you got 12 equals 2y, and then 6 equals 2y. Okay. So note that so far we haven't really had to consider multiple scenarios where like you might have a minimum and a maximum point. Okay, so far the equations are straightforward. Like look at the p equation. This equation, what type of quadratic is this one, Sarah? Concave up or down? And how do you know? Charlie, is this concave up or down?
Down.
Down. Why?
Because it's the minimum value and it's a positive y squared.
Not quite. If they ask for minimum value, it's concaving up.
Oh yeah, that's what I meant.
Yes, because it asks for minimum value.
Yeah.
But looking back at unit 1, the way to tell is looking at the y squared term. What's the coefficient?
Positive.
Yeah, yes, it's positive. So coefficient equals to 1, which is positive. Therefore, this will give you a concave up quadratics. Okay? If you were to look back at this one here, all right, let's have a look at this one here. So 10x minus x squared. Sarah, what's the coefficient of x squared?
Negative 1.
Yes, that's right. So this one has a coefficient which is -1, and that is less than 0. Therefore, this is a concave down quadratic. Okay, so you look at the coefficient of x squared in order to tell whether it's concave up or down. You guys will be dealing with quadratics a lot, like even in unit 3 and 4. Like my unit 4 students, they are like, oh, it's quadratics again. They're just so sick of it now, but they know how to do it. So yeah, so that will give you the y value. But is that the final answer? No, that's not the final answer. They ask you for the minimum value. So you sub y into the p equation again. So note that I'm giving you guys equation that looks strange, like py instead of y and x. The reason is I want you guys to get used to the idea of like the main variable, which is by itself, and then like the x kind of thing where you solve for. Okay, it may not be called x, it will be called whatever the hell they want to call it. Like they can't even call it y in this case. Right? It doesn't really matter. So the more types of equations you see, the less you will freak out when you see something like this in the exam. So sub y into p, then you get p equals to 6 squared minus 12 times 6, and then plus 16. So that would be 36. No calculator, Charlie. These questions are supposed to be done with a calculator.
It's just with a calculator, yeah.
No. The calculator questions are way harder. You don't get this question as a calculator question. So that's negative. So p is negative 16. Negative 36 plus 16 is negative 20. Okay, so always write the final solution. Therefore, minimum value equals negative 20. Okay, so what they're saying is that if you were to sketch a graph of x squared plus xy minus y squared, and you have a restriction where x plus 2y equals 4, that graph, because when you sub it in, you will get this equation, right? The y squared minus 2y plus 16 here. If you sketch this graph,
can you substitute into just like the original one as well?
You can, but then you need to find x.
Oh, like if I found x, can I just substitute?
Yeah, you can, yes. But if you have an equation that only has y in it, just sub into y, the equation that only has y, so you don't need to worry about x. You can find x, I mean, you already have a formula, 4 minus 2y, so 2 times 6 is 12, 4 minus 12 is negative 8. So if you sub x equals negative 8 and y equals to 6, you also should get the same minimum answer. Yeah, but we're not going to do that. So yeah, so this is the idea of finding minimum value. So this entire chapter is about minimum and maximum problems. Okay, so remember the basic steps. If you haven't noticed, or you should have noticed by now, is that the steps are always almost the same. Define the equation. You get an equation with one variable, and then after that, the steps very similar. Derive, set equals to 0, solve for x, and then you sub the you solve for the variable, and then you sub the variable in to get whatever the mean and maximum value they're asking you for. So far, these are abstract questions, which actually is supposed to be a bit easier, but because just because it's abstract, it turns out to be harder. Now, the ones that you most likely will get in the exam will be an application question, which is similar to question 4. Okay, but I'll let you guys walk through a similar question to example 9 first, and then I'll go through, and then we'll take a break, and then we'll go through the application ones. There's only one question in this chapter that looks similar to the example 9, because once you know how to do it, the rest, like any other question that you see, will be quite similar. However, the exam, they will not give you something so straightforward, or they might give you something like this, but then they could possibly throw it in like a weird location, and you look at that, you're like, what? How do I even do this one? So question 3. Alright, seems that you guys already know what to do, so I'm just going to slowly start working through this one.
y instead of x.
Same thing. You should get the same answer.
But when
then.
I did it, I didn't get the same answer.
You should get the same p answer, even if the y and like
What do you mean the
the.
same p answer?
You need to substitute the y into the equation to find p. You're finding the minimum value, not just the y value.
Can you look at it? Because I don't know where I went wrong.
Ah, that's 2y squared because y squared plus y squared. Alright, I'm gonna stop the first half of the recording now. Blake, if you're listening to this, make sure you do question 1, 2, and 3 before moving on to the second recording.